I'm pleased to be here today. And 10 years ago, we had our first meeting with archaeologists. It was in the cafeteria of Haifa University. Ilan was there. And everybody introduced himself, and they said, hi, I'm this and this, Iron Age. Hi, I'm this and this, Hellenistic period. And we were there, and they said, hi, we are from the 21st century. And in fact, this project, which is really, it's taking here for 10 years, what we have discovered during these years is that archaeologists not only explore the past, but they also do it in ways that belong to the past. And therefore, our vision is to bring archaeology into the technological revolution that we are experiencing these days. And replace some of the manual and extremely Sisyphean work that is being done today, as it used to be done dozens of years ago, some of which you can see here at the bottom. So this is a very high-level pipeline of the work of archaeologists from the point of view of me, that is, from the point of view of a computer scientist or an engineer. And so according to this pipeline, and let me say another thing, we're talking about the kind of sites which are completely destructed, that is, they went through a major disaster such as a war or earthquake or a fire or something like this. So what you can find in these places are little artifacts. So, and the way they work is say for 1 month a year, they go and they dig. They excavate and they find the little findings, the remains of what's left there. And then for the rest of the year, they're busy doing 3 types of tasks. The first is documentation. And there are many ways to document, but one way is actually to carefully draw the object that you find. So they have special artists who come to the excavation, and they choose a few of the artifacts because you cannot do it for everything. And then they draw the major things like you see here. And then they have to locate the object in time and in place. This is to say, where else in the world can you find similar artifacts? Because if they know it, they can know about cultural relationship, about commercial relationship, and so on and so forth. And this is done by leafing through thousands of pages of site reports and books in order to find something similar, as you see here. And finally, there is the task of reconstruction, where the goal here is to bring those artifacts back to life, to make them look like they used to look before they went through the disasters. But when we looked deeper into this process, we found out that those tasks are actually classical computer vision and computer graphics tasks. When we talk about documentation, this is edge detection and non-photorealistic rendering. When we talk about location, of course, this is Google. This is matching. You do similarity and retrieval and classification. And we're talking about reconstruction. These are the kind of tasks. This is puzzle solving and hole filling, and so on and so forth. However, when we try to apply the classical algorithms, we failed miserably, because this type of objects are not these natural images or nicely behaved 3-dimensional CAD object. They are really bad. They are extremely noisy and eroded and broken. So this was a challenge. And through this challenge, we thought, OK, we can maybe change archaeology, but on the same time, advanced computer vision or computer graphics because of these new algorithms that suit this special type of very difficult objects. We did work on all these tasks, but today I'm going to focus only on reconstruction. But before I describe what we did, let me say a few words about the collaborations that we had. We have been working with two groups of archaeologists. The first of which is the archaeologists from the University of Haifa and the Hebrew University who are investigating Dor. And the second one, this is a group of archaeologists that is investigating salamis in Cyprus, mostly in the British Museum at the Cyprus Institute, and this work was done under the H2020 Gravitate, a European project. So first, let's see Dor. So you all know where Dor is. It's southern of Haifa, and you've probably been there because it is such a beautiful beach, maybe the most beautiful one. But maybe you saw there this little hill. And this little hill is actually an archaeological site. From this aerial view, you can understand why Dor was so important. To the north, there is a little bay. And to the south, there is a very large lagoon with little islets that protect it. And prior to the invention of artificial harbors, when you wanted to sail from Phoenicia, Lebanon of today, to Egypt, you had to stop somewhere in the middle. And Dor was an ideal stopover. And therefore, everybody ruled Dor, starting from the Canaanite at the late Bronze Age, and the Sea People and the Israelites, which means the United Monarchy under King David and Solomon, and Assyrians and Persians and Greeks. And finally, the Romans arrived in Israel in 63 BCE and stayed here for 250 years. And then Dor lost its importance. It's speculated that the reason for this was because it is the Romans who invented artificial harbors, and then they built Caesarea, so the need of Dor was not that important anymore. This is the type of artifact that you find in Dor. So you can see at the top left, you can see a silver Hellenistic coin. To the right, you see an Hellenistic oil lamp. At the bottom to the right, you can see a Phoenician pottery vessel from 11th century BCE. It was produced in Dor but found in Cyprus. In the middle, you see a cup, a drinking cup shaped like an African from the Roman period. And maybe the most beautiful one is the one to the left, which is an Iron Age seal. It's early Hebrew script where it says Kohen Dor, the priest of Dor, and you can all recognize the delta of this Dor. When we talk about salamis, this is the type of findings that you find. They're all 2,500 years ago. And today, the findings from salamis are dispersed across 4 museums. In the British Museum, in the Ashmolean Museum, in the Fitzgerald Museum. One is in Oxford, the other one is in Cambridge. And some is still left in Cyprus, in the Cyprus Museum. And they dispersed it in a way that you don't have the full object, but rather one museum has the legs, the other one has the head, and so on. Okay. So this is the little introduction to the people we work with. And, but before we go into our contribution, I want to say a few words about the representation of the object that we work with. The common representation is an image. So you see here an image of a two-dimensional representation of an oil lamp from Dor. So you know what an image is. But we often do not want 2D representations, but we want the whole object. And in this case, we scan the object, and we have the 3-dimensional objects, which means that our problem is a geometric object and this object, as you see, has geometric characteristics. We're going to touch it later on. So I said that this object was created by scanners, but actually what scanners produce are point clouds, such as this one. This is a point cloud of a torus. So it's a sampling of a surface, okay? So in the previous representation, we talked about a surface that is the external surface of the object, and now we have a sampling of the surface. And you can see here that sometimes it looks quite funny because points cannot occlude each other, and therefore you can see through the back and the front. And during this talk, depending on the task, I'll keep jumping between two-dimensional, between images, and three-dimensional, that is surfaces and point clouds. So I said that today I'm going to focus on reconstruction, but what does it mean, reconstruction? We partition this general task into 5 subtasks. Okay, reassembly, hole filling, reconstruction from drawing, colorization, and document enhancement. And the way I build this talk is that first, I'll go pretty quickly through the first 4. I'll mostly show you results and key ideas, but then I'll dive into the 5th one and give more details, more specific details about the algorithm itself. So we start with reassembly. And in order to motivate this problem, look at this. This is a picture that I took at the basement of the British Museum. Okay, so when you go to the British Museum, you've all visited there, it's huge. And still, it turns out that the vast majority of findings has never been displayed and will never be displayed. So the basement is extremely important because 95% of what they have is actually in the basement. And this is how the basement looks like, drawers and drawers and drawers of artifacts. And here you can see, these are the artifacts from Salamis. Okay? You can see also the archaeologists from the British Museum we collaborated with, but also you can see quite beautiful artifacts, and you can see the fragments that people they were never displayed nor reassembled. Okay, so this was the major challenge. How is it being done today? You can see here an example that I took from the internet. Okay, so quite a few restorators have this table with all these fragments, and they glue the pieces one after the other, and if they make a mistake, they have to unglue. And this process, depending on the size of the artifact, can take days and weeks and sometimes more. But instead, we can look at this with our eyes. And when looking at this with our eyes, this task is actually puzzle solving, jigsaw puzzle. And when we look at this way, we can define the problem. So this is our problem. We would like to reconstruct an object from a set of non-overlapping and unordered parts. That's our task. And it turns out, so every kid knows how to do this, right? At the age of 3, they're already solving jigsaw puzzles. But it turns out that this problem is quite hard. It's actually an NP-hard problem. But still people wanted to work on this. And when we looked at the literature, we found out that most of the work on puzzle solving was done on images. So the way it was defined, let's take an image, cut it into square, equal size square, and then let's try to solve it. So when we saw this, we said, OK, let's take it step by step. Suppose that we know how to solve the first one. Now we would like to take the same square parts of natural images, but add other requirements, the requirements that suit archaeology. And after that, we can actually take images of real artifacts. And finally, we can go to solve the problem in 3D. And let me say that in 3D, there are a couple of groups around the world that work in this domain. So let me go through these two stages and show you some examples. For the second step, we said we still have equal size squares of a natural image. But now we're going to add two additional requirements. One is that we're going to have missing pieces. That is, we are not going to have all the pieces of the puzzle. And the second one, that pieces from a variety of puzzles are going to be mixed together, because this is the way that fragments are found. Okay? And as I said, I'll show you some results. So you can see here a result of, we get 5,000 pieces. That's the input at the top. And at the bottom, you can see our result. Out of these 5,000 pieces, we have built 5 puzzles. The black squares, these poppy seeds, are actually the missing parts. So the puzzles were built flawlessly. And the way, I'll show you a little movie that shows the process. So this paper had a few key ideas. The first of them was that you have to carefully choose your first piece. Because remember, the problem is NP-complete. So you have to use heuristic. And if you don't do it carefully, you're going to err. Previous algorithms just randomly chose a few pieces and solved the problem multiple times and let the users decide which solution is better. So here, and another key idea is really to choose a very good similarity function. And what you see here is that when you do not have a similar enough piece, you start another puzzle. So now we started the 3 puzzle. It doesn't mean that at the end we're not going to complete the rest of the puzzles. Okay? So now you can see in a second that additional puzzles are going to be added to the first and the second images. Here's another example. So to the top you see we have 13,000 pieces. And at the bottom, you see our results. After the 13,000 pieces, we have built 3 puzzles with missing pieces. And you can see that these are pretty difficult puzzles in the sense that we have lots of whites in these images, and still the results are pretty good. The puzzles were built flawlessly. So this was our the first item. As I said, first we said, let's take what people knew how to do and add our requirements. We are still working on natural images and square size pieces. But now we wanted to move to archaeology. Still in images, but in archaeology. So what are the additional challenges that we had to deal with? The first one was that there is abrasion of the pieces. And this abrasion creates gaps between the pieces. As you see here, they're not going to be connected well. And especially, most of the abrasion is at the edges, while all algorithms for puzzle solving used only the boundaries. This was the only thing they considered. So this is challenge number 1. Challenge number 2 is that the color fading that happened over the years results in spurious edges. And these edges had to be distinguished from the real edges and gradients of the colors that are important to perform similarity between the pieces. And finally, the value transformations between every 2 pieces belong to a continuous space rather than 16 possible transformations between 2 pieces that we had before. Okay? So this was the challenge, and we worked on it. And when we were done, we put it on archive, of course, as everybody does today. And the next thing that happened was that a friend from Ilan from London sent us this piece from the Times. And this piece says, AI's answers to Indiana Jones picks up the pieces from broken treasures. And they describe it papers. They never interviewed us. They interviewed archaeologists to explain how important this thing is, and so on and so forth, but they put images from our papers, and we'll talk about these images in a second. And after that, it appears everywhere in London, in La Repubblica in Italy, and elsewhere in the world. So this is very nice to us. So what were the key ideas of this paper? The first idea was to address abrasion by doing extrapolation of every fragment by itself. So this has, in other words, not only we predict how the fragment looked like before it was abraded, but also it reduced the problem of continuity of how one fragment continues into the other, into the problem of matching two fragments. The second idea was that we have to find a way to sample the space of transformations, because, as we said now, we do not have only 16 transformations. And we came up with a technique that is based on configuration space from robotics to do this. What you can see here is that these two fragments are considered valid, okay? But these two are invalid because they're too far from each other, and these two are invalid because they overlap each other. The third idea was, of course, to come with a good dissimilarity measure, a dissimilarity measure that suits the specific domain of archaeology, where you know that on one hand you do not have many colors, but on the other hand, the same color does not look the same when you have abrasion, where the length of connectivity differs, and so on. Let me show you a few results. So you can see here a few reassemblies of fragments that we got from our partners. But after we did this, they said we don't have any more examples to give you with ground truth, because either they are already assembled and then you cannot reassemble them, or we don't know whether they can be reassembled. So this was a problem. For us, we needed to have data. Okay, this was the question: how to create more examples. We suggested to them, we said, we can just randomly have cuts over the object, and they say, no. Random cuts are not archaeology. And then we came with this idea that they said, okay, this can work, and we used dry mud, okay? And the idea of dry mud is, first of all, it's natural, it's not random. And it has gaps of various widths, and we can just remove fragments if we want them, if we want to have holes. And color fading would come from the object themselves, like this, okay? So we can have those, and the color fading exists here. Once we have this, we could check our algorithms on as many objects we wanted. And you can see here some examples. Here are more examples. We just took them from the web, and more examples. And to the right, you can also see a drawback of our algorithm, where these two were connected, but it had to go there. OK. So this was our work on reassembly, or on our puzzle solving. And I'll move to the second task of hole filling. Archaeological artifacts often contain holes of missing geometry, which are not necessarily a result of the scanning process, but they come from the source objects themselves, as you see here. Okay, and the question is how to complete these holes. This is what archaeologists are doing. I said they invite an artist, and the artist draws the object, and once the artist is doing so, she also completes the hole with these dashed lines that you see here. So we were thinking, now how are we going to do it ourselves? And for this problem, we're not working on images anymore, but we're going to do it in 3D on scanned object. For 2D, if we wanted to work in 2D, we could go back to the very best, to curves that are called Euler spirals, who were discovered independently by Bernoulli, by Euler, and by Talbot, to use them to design railway tracks. Okay? And the nice property of this curve is that the curvature evolves linearly along the curve. There is some psychological research that claims that these curves are very good for the human eye, that it's better than other types of curves. And therefore, Kimia, in 2003, used them to complete images. We wanted to define a new type of curves, which we call 3D Euler spirals, that will be very similar. However, they'll do it in 3 dimensions. And you can see our Euler spirals now, where they evolve from the plane upwards. And this curve, we defined it to be the curve that penalizes for the change both in curvature and in torsion. It turns out that in these curves, the curvature and the torsion evolve linearly. Both of them evolve linearly along the curve. And therefore, we could prove that they satisfy several properties that are considered to be eye-pleasing. And these properties involve invariance to similarity transformations, and roundness, and smoothness, and symmetry, and a couple more. Let's take an object that is similar to the drawing I showed you before, and you can see how these curves complete the 3-dimensional surface that we have here. We actually have a drawing of the surface, on top of the surface, and the completion. Here's another example in which you could compare our completion to the classical Hermit splines, and you can see that it looks completely different. In fact, we have perfect circles that complete the curve. They are in 3D. And this comes at no surprise, because one of the properties that we proved in this paper is called roundness, which means if your end conditions lie on a circle, you're going to get a circle. We did not stop here, and we completed also surfaces. You can see here the result. And note that you cannot just copy from one place on the surface to another, because this oil lamp, I have a replica of it here, so you can see more or less the size. And this thing, the width of the circle here is different from the width of the circle here. This cupid here is not at all the same cupid as there. So you have to do something different. Here's another example with where you see the same thing. It looks like you have all the stripes which you could copy, but each of the stripe differs in texture, in width, in its geometric properties. Just to illustrate it on a surface that is considered to be very complex. This is an artificial hole, of course. To the left, you can see the original, and you compare our results to others, and you can see that the structure of the eye was recovered pretty nicely. The third task, which I'm just going to show you images, is called reconstruction from drawing. We said at the beginning that the archaeologist invites an artist, and this artist draws this artifact. And this is the kind of drawing. They are really, really beautiful drawings. However, the artifacts themselves, you cannot access them anymore. Why? Because they are locked away in drawers, in museums, in boxes, in storage, and so on. So the only thing you can access is these drawings. And the question we have is whether we can at least virtually create these drawings, the object, out of these drawings. And let me show you a result of this. So this is the result of this input, which consists of 500 curves. I said I'm not going to go into the details of the algorithm, but still, an interesting thing about it is that the major part of the algorithm is reducing this problem to the problem of topological sorts that we study in basic algorithms courses. Here is another example. To the left, you see the input. And to the right, you can see a reconstruction from these curves. The fourth task is called color reconstruction. And here, we move again to colors. Okay? So we started from colors in puzzles, and then we moved to the geometry. And now we're back to colors, but to colors on surfaces. What does it mean? The common perception of the large Greek and Roman statues that we have is that they were all pure, unpainted stone, this white thing. But many researchers claim that this was not at all the case, that these statues were full of color and vibrant and beautiful, like this. Okay? This is not our doing. This is from a museum where they took an artist and they told the artist, please add color to the statue. What happened to these colors? During the years, they disappeared. And the little pigments that remained were washed out when doing the cleaning. But if we had these little traces of pigments, we could reconstruct this. And how? I'll show you a session. So you can see here, the user adds some scribbles over the surface, chooses colors. If we knew the real color, we could use them. And then the system knows how to propagate the colors on the surface, preventing bleeding from one piece to another. So you can think about this problem as interactive segmentation, in which you can fine-tune the segmentation as you progress. And you can see now how the torch is being recolorized. And this is more or less the end of the session. And so let me show you a few examples. So you can see here you have a few patterns which are the same. It's enough if we just have a few strokes around one pattern, and it will propagate to the right. This was the most complex example that we had. It's very complex because there are lots of figures. They're holding each other. They're holding things. They are dressed differently, and so on and so forth. So we used 50 strokes, and it took about 10 minutes to bring this thing back to life. OK. So now we're going to the last task. And as promised, here I'm going to go into details of the algorithm. And the reason I like all of these tasks, but I especially like this because it involves 2D and 3D, as you will see. And also, it relates to problems that are seemingly completely unrelated. And so I think let me first define this problem. This is the input. What you see here is a letter, a medieval transcript written by some bishop. And you can see that it's badly stained. And it's stained due to ink spills and degradations that happen over time. Our goal is to automatically extract the text out of it. That is, this task is called text binarization, and this is what you get. In other words, you get this gray level image, and now you want to create a black and white level, distinguish between background and foreground, text and the rest of it, okay? So this was the state-of-the-art output before us, and this is our result, okay? Again, state-of-the-art, our result. So you can see that a lot of text below the stain disappeared, and it reappears with our algorithm. How did we do it? I'll go top-down. So that is, when things are still vague at the beginning, they're going to be cleared later on. The idea is the following. We have a problem that is a two-dimensional problem. We have a document, an image of a document. We have pixels. Now we take these pixels and we represent them as points in 3 dimensions, okay? Such as the torus that we saw at the beginning, okay? So we take an image, and now we have a point cloud. And on this point cloud, we detect the visible points, points that are visible from a viewpoint. I'll define it more rigorously in a second. And it turns out that this simple operation reveals information, hidden information, about the image. And this information will allow us to distinguish between text and no text, okay? So these are the two things that we're doing. We are representing an image as a point cloud, and we detect the visible points in this point cloud. Okay. What is the intuition of this representation of a point cloud? We are going to create a representation that is doing this. So remember that a point cloud can be considered as a sampling of a surface, okay? And a surface, you can think about a surface as a terrain. And a terrain is valleys and ridges, okay? It's a geographic terrain. And so given an image, we're going to make sure the text is going to appear in narrow, deep valleys in the 3D point cloud. The background is going to be on elevated plateaus. The stains are going to be in structureless terrains, and stains on the background are going to be on shallow valleys. Or in other words, okay, when you have black on white, it's going to be in valleys, okay? But the text is going to be in deep valleys, and the stains are going to be on shallow valleys. And it turns out that the visibility operator that I'm going to describe in a minute can distinguish between deep valleys and the rest of the image, okay? So this means that our algorithm has 4 steps. First, we transform each pixel to a 3D point, okay? Pixel, point. Second, we detect these visible points. And once we have this, so what you can see here are the visible points, okay? So some of the points are visible and some are not. But maybe you can already see that there are many visible points along in the background and in the vertical stain, in the vertical crease here, but there are not many points, if at all, on the text, okay? So based on this, step number 3, we create a visibility-based image. So now we have a new image. And you can compare the original image and the new image. So this image looks much better. Text is better separated from the background. And given this image, we just give it to any state-of-the-art algorithm that knows how to do binarization. Okay? We're going to go deeply into this process. So the first stage, we said, we're giving an image, pixels, and we're going to transform them into point cloud. How are we going to do this? We're going to take this image and first of all paste it on a portion of the sphere. Paste it on a portion of the sphere. Okay? That's easy, right? We use the polar coordinates and we're doing it. And once we did it, we start pulling each point. We're already in 3D. We're pulling each point towards the center of the sphere so that the more black a point is, the deeper it is. Okay? So black pixels are going to be deeper in this representation. This is the point cloud that we are going to create. If we look at this orange curve that goes through the image, okay, what's going to happen here? This is the representation in 3D. Text is going to be in deep valley because it's really, really black. The crease, which is wider and not as black, is going to be in a shallower valley. This is stage number 1. In stage number 2, we are doing visibility detection. And again, you can see here that the density of the visible points on the crease and on the background is much larger than the one on the text. Okay? So this is the trick. So why should visibility work at all? For this, we're going to take a break from document enhancement and talk about visibility. What is visibility? Suppose you have this set of points. This set of points represent a gear. Because it's point and it's not surfaces, remember when we had the torus, you can see both the front and the back. Okay? In this sense, it looks so funny because on one hand, you can see the front. This is the mouth and the skull. And you can also see the back. This is the hairdo at the back. And this happens because points cannot occlude each other unless they accidentally fall on the same ray from the viewpoint. But if you have the viewpoint here is you, okay? If you could distinguish between points that should have been visible to those who should not, the front from the back, this is the image that you would get. Now you can see that Igia is actually looking forward. To define this problem properly, we're given a set of points, P, which is considered to be a sampling of a continuous surface and a viewpoint C. And our goal is to determine the points that are visible from C. In other words, the point that would be visible if the surface existed. What's the classical way to solve it? Take a set of points, reconstruct the surface, and then find the visible points, because once you have a surface, it's easy. You just send a ray, and the first point the ray hits, that's a visible point. Okay? But the question we asked was whether visibility can be determined without reconstruction, because reconstruction is a very complex process both theoretically and implementation-wise, that usually requires lots of additional information, such as normals and sufficiently dense input. And surprisingly, a few years ago, we answered this question in the affirmative. In a sequence of papers, we proposed an operator called the HPR, the hidden point removal operator, that performs exactly this. Okay? Given a point cloud, it finds the visible points, the points that would be visible if the surface existed from this sampling. And though the proofs of why this operator works is quite complex, the operator itself is inherently simple. To implement it, it takes only 8 lines of MATLAB. Okay? So let me tell you what it's doing. So what this operator is doing, suppose now that this is your point cloud in 2D. Okay, so the blue cat is your point cloud. What in the first phase of the algorithm, you project this point cloud around about a sphere. So the result of this transformation is this red point cloud. Okay. In fact, this sphere has to be much larger, but this is only for illustration. So you send a ray through this point cloud, and you transform it using a function. Very easy linear transformation. Once you have this red point cloud, you construct the convex hull. You construct the convex hull of the viewpoint and the transformed set of points, the red cloud. You construct, so what you see here in black is the convex hull. Okay? So let's copy this to the next slide. So what you see here, you see the convex hull of the transformed set of points. And it turns out that, like magic, points that fall on the convex hull are the visible points. Okay? These are the points that fall on the convex hull, and they're all back projections of this part of the cat. Okay? So this is what the operator does. This operator has lots of advantages. It's correct in the limit. It has theoretical guarantees for sampling. It's very efficient. It's very simple. But for our case, we are doing document enhancement today. So for our application, I'm going to consider only this. Okay? This operator, if you had infinite set of points, the operator is going to be correct. Okay? This is number one. But if you have a sampling like we have, then we can only have theoretical guarantees. That is, we know when the operator is likely to err. And these theoretical guarantees say that a point is guaranteed to be detected visible as long as it's indeed visible and its curvature holds some threshold. Ignore what it says in the threshold. But what it says is the following, that remember, we had an image, and in this image, we moved the points. And all the points should be visible. But the operator is not going to find all of them. Which one is it going to find? This theorem says that a point is guaranteed to be detected visible as long as it's indeed visible, and its curvature holds some thresholds. Or in other words, our operator is going to be correct if our points are on ridges or are in shallow valleys. So this limitation comes to our benefit. Why? Because what this theoretical guarantee says that if we're going to err, we're likely to err in deep valleys. Okay? But what did we put in deep valleys when we did the 3D representation? We put there the text. Okay? So our operator is going to miss the text, but find everything else. And therefore, we are back to this, and you can see the result of the visibility operator. It's going to miss the text. We don't have red points along the text. We're going to have red points everywhere because the background is on ridges, on these plateaus, and the crease is in shallow valleys, and only the text is in deep valleys. And therefore, in step 3, what we are doing is, given the point cloud that you see here, we look only at the points that the operator found, and they are marked in gray, and we interpolate them. Okay? Whatever the operator did not find, like the text, we ignore. When we do it in 3D, this is what we're going to find. Okay? We're going to produce this image, the image without the text at all. So we're almost done because take the original image we subtract this visibility-based image, and we get the results that you see here. And already you see that this image is much nicer than the other one because the text pixels are closer to each other, and they are better separated from the background and the crease. And in the last stage, we just give this image to an existing algorithm. So people who are doing binarization, they usually have very special tailored algorithms to do binarization that consider the fact that this is text. And we do not compete with them. We just tell them, OK, use our image instead of yours and do this. Let me show you examples. To the left, you can see a document. And to the right, you see what two different algorithms did for this letter. And here you can see our result using the very same algorithm. So each algorithm is improved compared to itself. Okay? And this big stain disappeared. Here's another example. And again, given to two algorithms, you can see here that this was the original result, this is our result. And you see that the big black stain there disappeared. Another example where you can see that the crease disappeared, but the original result ignored this word. In our result, when using this algorithm, this word reappears. OK, this community has standard benchmarks and data sets and so on. So even quantitatively, we improved the results. What's important, whenever they did well, we improved a little bit because they already did well. But whenever they didn't do as well, we could improve more. Okay? So, and this was important. Now, it turns out that in this community, they have a competition. Every year or two, they have a competition. And you send them the code. And the code that wins gets prizes and so on. So what we did, we took the code from the winner of the previous year. We added ours. We sent the code. And we got the first place, of course. So every 2 years, we can make the first place. We take the last code, the last winner. We add our pre-processing. And we are done. OK, so let me recap. So I showed you today results from 2 tasks of reconstruction, focusing more on the last one. I want to go back to the vision. Really, archaeology today is reaching an impasse in its ability to handle the vast amount of data that they have. And really, our vision is to make this science, archaeology, a modern science. As I said, we did works here and here. I'm not going to discuss them, but I'm going to show you one result from each. So this is an image that we saw before. And this is a non-photorealistic result for the same image. It's in 3D, actually. And you can see here that some features come to life. Okay? You can see the facial features. You can see the hairdo. You can see many things that you could not see in this really distracted object. What was done here, we took the oil lamp. This is a picture. We took the oil lamp, we scanned it, and we applied our algorithm. And another result from the third task that maybe suits Google more than anything is searching. Okay, given a query like this, we could find them on a different object. This talk was based on many papers. I said it's work of 10 years. I listed only the reconstruction work, not the ones on documentation and similarity. And lastly, I want to thank many First of all, the students who did all the hard work, and there are many of them because each one of them worked on different tasks. And my partners, Ilan, who is sitting here, and Eitan, who is sitting in Colombia, and the archaeologists, and of course all those who gave us the money to perform this research. Thank you.
Thank you, Ayellet, for a wonderful talk. I have maybe we have just a couple of minutes for questions.
Hi, thank you for the talk. About the document reconstruction, I know you can't argue with results, but I couldn't help thinking, well, so the deep valleys, the deep narrow valleys, they are just high frequency features. So couldn't you get like similar results by just trimming the high frequency features from the image?
Actually, we tried it as a first, the first file was this, right? And we couldn't. Let me say a few words about this. I presented it as something only for archaeology, but actually this algorithm works also for new stuff. When you take a picture with your cell phone, you have all the shadows that you want to remove, and we do it better than the state of the art with the exact same algorithms. Okay, so and there are lots of other image enhancement that the student did, but I didn't present them. So it actually is more general and performs better for this specific application and for other applications.
So I was wondering, for the 3D reconstruction, have you tried actually reconstructing something from an algorithm, like feeding some point cloud, having it reconstructed, and then actually trying to assemble the object?
You mean the puzzle solving?
Yeah, but with something that's actually 3D, where you have pieces, you scanned it, it was reconstructed by the computer, and then actually trying to glue it together.
So this is a current work. I said we have 4 stages. The first one we didn't touch because other people did it. We did 2 and 3. And Ilan, as a student who tries to do exactly this, it's very, very hard. Okay? It's very, very hard. It's much harder than dealing with images. But obviously, this is the next step. Okay? This is the next step, scanning everything and doing it. Maybe I should say something else about the scanning process. Because the big thing today, I think, is that you're going to have data. I talked a little bit about this in images. But if you don't have enough data, then you cannot do any of the things. So, and the scanning, who is doing the scanning? So for this European project, there are 2 groups of archaeologists, the British Museum and the Cyprus Institute, and this was their job. For 3 years, they had to scan stuff, okay? This was exactly their job. Because if you don't have it, and people in the various groups around the world do not do it, then you're not going to, you're going to have 2 vases, okay? What I said, it's current work. What did we do? We took artifacts. We gave it to the lab engineer. We told him, please try to reconstruct them. We printed them on the 3D printer, and the lab engineer reconstruct. So now we had the ground truth. Now we could work. But for how many objects are you able to do it? Unless it's spread all over the world and all the groups of archaeologists give you such data, it's going to be very complex. You're going to have an example, 10 examples, but that's it. Okay? That's in general a problem when you come to archaeology.
Hi. So I'm curious how deep learning wasn't mentioned throughout the whole talk. So did you consider in any of these tasks?
Yeah. So actually, we have a new paper for puzzle solving, but in 2D, that is doing deep learning. It's doing better than our first algorithm, the one with square parts. Okay. It's doing better when you have gaps but it's not doing better until now when you don't have the parts. But let me, when you don't have gaps, but let me say maybe something else. Okay, I think my view, as one who likes 3D, that this is the big thing now in deep learning. Okay, how you're doing deep learning for 3-dimensional data. Okay, so there is lots of work, and we're doing part of it. But this is still the big challenge. It's not working as well as it's doing in images. Okay? So if you want to know where, in my view, where deep learning is going to go, this should be a focus. If you're going to have more and more scanning, this is what you should do. Okay? And so I have a variety of students today who work on basic geometric problems using deep learning, hoping to do better. For similarity, currently we beat all the deep learning algorithms in 3D, okay? But it's not going to last much. It's going to end. I mean, when we have better deep learning algorithms for geometry, we're going to lose. But it may take a year or 2 or 3.
We're already there in 2D.
In 2D, I mean, in 2D there is a revolution. I mean, no other algorithms can beat. It's the focus on 3D, deep learning for 3D. This is not yet a solved problem.
Okay, so thank you, Ayellet. That would be it for now. Thank you.